Okay, so we're in chapter 3. We're starting by talking about the difference between a power function and an exponential function. A power function is a function that x is being raised to a number. It's being raised to an exponent that is an actual number, being raised to the second power, being raised to the fifth power, being raised to the seventh power. An exponential function is where a number is being raised to x. So since it's exponential, x is my exponent. So that's kind of how we can tell the difference between these. If it doesn't fit either of those, then we just call it neither. So looking at the 4 examples I have, the first one is an example of a power function because it's x being raised to a power to an exponent. Letter B, y equals 3 raised to the x. Well, that's an exponential function because x is my exponent. Letter C is y equals 4 squared. Well, where's my x? There's no x involved, so this is a neither. And then letter D says y equals x raised to the x. Technically, that's following in both of the boxes, but neither of them has like more power over the other and like reigns supreme. So we just call this neither. It doesn't really fit either of them specifically, so we don't call that either type of function. Why are you still up? There we go. Okay. All right. Now we're going to do some plugging in. So I was telling the class yesterday, I feel like exponential and logarithmic functions are something that we talk about like every year. We talk about it a little bit in Algebra 1, a little bit in Algebra 2, and a little bit in PreCalc. And I feel like as teachers, we kind of blow it off. Like it feels like it's always like the thing we like squeeze in at the end. So I know personally, I feel like this is like my weakest part of like my math knowledge is because exponential functions were never really fully discussed. So it might feel like a little bit of a review at the beginning, and I'm sorry I'm doing it literally again where I'm like literally plugging it at the very, very end of the semester where like there's no time to do this. So if you are confused or have questions, please make sure that you ask them. Nothing is a silly question or something you should already know because as I said, I feel like we just always like push this at the end and then we don't give it the full, I guess, respect it deserves. Okay, so number 2, find the value of the function for the given x. So I'm plugging in all of these x values into my functions and solving. So we'll start with the first one, 3 times 5 raised to the x. So I'm doing 3 times 5, and this time x is 0. I'm glad we're talking about this one at the very beginning because it's a concept we're going to keep using. Anything raised to 0 power is 1. So you can essentially cross it out, and we end up just getting 3. 3 times 1 is just 3. Next one, we're looking at where x is -2. So I've got a whole new function. I've got 6 times 3 raised to the -2nd. Remember that a negative exponent makes it into a fraction. It flips it under the fraction bar. So I've got 6 times. My 3 squared goes in the bottom of a fraction. And then now I keep going from there. I do my 3 squared, which is 9. You're welcome to cancel at this step, but if you don't, you would have 6 over 9, and then I would have to cancel here. I've got 3 in both of these terms, which leaves me a 2 over 3. So my final answer is 2/3. We often get fractions in this unit because we're dealing with exponents, and every time you have a negative exponent, it goes into a fraction, so that's common. Any questions so far?
On the first one, how is that 3?
So 5 raised to the 0 power is 1. And so I've got 3 times 1, which will stay at 3. Does that help?
Yeah, I thought they were, I thought it was like 3.5 and like 6.3 and stuff like that. But
Yes. All those multiplication signs, if you would rather, you can put them in parentheses. Yeah. If it was 3.5, then Jared would be right. It would just be 1 because I would get rid of that whole number, that whole 3.5. Okay. The next one, I have a fraction as my exponent. So let's go see what that fraction does to my problem. I've got -2 times 3 to the 1/3. Well, a fraction as an exponent makes a radical. Normally our radicals are square roots. Now -2, nothing's happening to it. It stays the same. But that 3 goes under a radical. The 3 on the bottom of my fraction goes, it like defines the radical. It makes it a cube root instead of a generic square root. Technically, the 1 on top would go inside with the 3, but I'm not physically writing 1 because it's redundant, it goes away, it doesn't matter. So in a fraction as an exponent, the denominator goes over the radical, so it defines what kind of radical I have. The base goes under the radical like normal, and then the numerator of my fraction goes inside with the number under the radical. I'm going to simplify this if I can. However, on this one, if I'm going to simplify a cube root, I need something times itself 3 times. I need like 3 times 3 times 3 in order to pull it out of my radical. But 3 by itself doesn't have other factors. It's as simple as it gets. So the simplest this one goes is -2 cube root of 3. We're about to do another fraction one, so if you're still a little confused, hold tight because maybe the other fraction will help clear some things up. The next one is 8 times 4 raised to, in this case, sorry, I can't do 2 things at once, guys. This time it's being raised to the -3/2. So I've got 8 times 4 raised to the -3/2. Oh, that's a mess. Again, I can't do anything to the 8, so it comes over here. My base of 4 goes under the radical. My numerator goes inside with my number under my radical. And then the denominator 2 would go out front. However, like I just said last time, it would be redundant to write 3 to the first because we know 3 to the first is just 3. It's redundant to write a 2 out front here because a radical by itself with no number defining it is a square root. And a 2 would just confirm that it's a square root, and that's extra step that we don't need to write. So we're gonna leave it like this. I've got my 4 under the radical, I've got my -3 with the 4, and I've got the square root. Again, I don't need to physically write the square root. I gotta do a couple things here. So first thing I'm gonna deal with is that negative. Since I've got a negative exponent, it's gotta go in the denominator, and I'm taking it all down with me. So I've got 1 over radical 4 raised to the 3rd. Now I just keep simplifying like I know how to. I'm gonna do 4 to the 3rd, which is root 64. Oh, and then I can simplify that. Root 64, oh, that's actually a perfect square. I've got 1 over 8. And I'm multiplying 8 times 1 over 8, which cancels out, and I get 1.
Miss White, does that negative with the exponent just make it a fraction, just flip it?
Mm-hmm. Yeah, so the negative made it flip, which is why on this step I went down to the bottom of the fraction. The 3/2 made it a radical, a square root with a cubed underneath. Any other questions on this problem or any of the 4 we just did?
You know how you said it's like redundant to write if there's a 2?
Mm-hmm.
Can I still do it, like, at least for the first step?
Yeah.
Will you take off for that?
I wouldn't take off. It's like writing 1x, right? Like maybe when we first started, we had to do it to remind ourselves. So same thing here. If you want to write 2 to remind yourself, then that works. Sometimes when we have a 2 in this step and then we don't have it in the next step, we're like, what happened to that 2? So feel free to write it. You just don't have to.
Okay, thank you.
You're welcome. So we just went over a lot of exponent properties. Any other questions? You guys are asking good ones today. Okay, the next problem is saying write the equation of an exponential function where, and then it gives us two sets of points. F of x, or f of 0 is 3/2, and then f of -2 is 1/08. We've done this with lines, with polynomials, with quadratics. Now we're doing it with exponentials. What I need to give you first, though, is the general way we write a exponential function. So generally, we write it as y equals a times b raised to the x. Just like when we did quadratics, we did y equals a x minus h squared plus k. Like, those are just general forms we use. If you hate using the dot like I am using right here, you can do little parentheses if that makes you happier. Go for it. So I have two points, and so I'm going to use the first point to find a, and then I'm going to use the second point and a to find b. So I'm carrying this over. I've got y equals a times bx. I'm just rewriting it right here where my point is. So I've got 0 and 3/2. And so I'm just going to replace x and y with 0 and 3/2. It's just a weird 3. There's no negative there. Oh, this is perfect because 0, anything raised to the 0 is 1. And so I'm just left with a on this right-hand side. So that means 3/2 is equal to a. Hint, most of them will work like this. I'll give you a 0 point and then we'll find a very easily, and then we'll use a new x and y that are both actual values and not 0 in order to find b. So if a is 3/2, I've got, I'm going to rewrite my formula again. Y equals a times bx. I'm going to put 3/2 in for my a. And now I'm using this new point of -2 and 108 in for my x and y. So x is -2, y is 108. That's really the new step. Everything else now is algebra stuff. So the first thing I see is I've got this negative exponent that I don't want. I'm going to simplify that to just be 1/b squared. I'm going to combine the fractions just because it's an easy combination. And it simplifies, it cleans up that right-hand side. And then now you have two options. You can either just multiply that 2b squared on both sides in order to get rid of it, or you can physically cross multiply. It's the same math, so it's not incorrect one way or the other. Some of us like to do cross multiplication, so you think of that a little bit more obvious, but at the end of the day, we're still gonna get the same thing, whether you do it by multiplying by 2b squared on both sides or cross multiplying. I'm gonna get 3 equals whatever 108 times 2 is, which is 216 b squared. Divide by 216. Don't have a lot of space, I'm just gonna keep bringing it up. You can make it a fraction, you can make it a decimal. The only thing is a decimal is not gonna be as nice. You're gonna get a weird, a really weird decimal in a little bit, so I'd rather you keep it as a fraction right now. 3 divided by 216, I'm gonna leave it as 1/72 equals b squared. We need to square root both sides of my equation to get rid of my square. Square root of 172. Well, that top one is perfect square, so I'm gonna leave it as just 1. But I do have a root 72 in the denominator. We're in pre-cal and we can't leave radicals in the denominator. We can't unrationalize a problem, so we need to do our work to get this rationalized. Let's make a little chart off to the side. Let's simplify this radical by doing our little factor tree. And then any denominator that's still a radical, we're gonna multiply it on top and bottom to get rid of it. 72, I think that's 2 and 36. Oh, that's perfect. I have a perfect square right here, 6 and 6. So I can take 6 out of my radical, and I can leave 2 on the inside. So this gives me 1 over 6 root 2. But I still have a root 2 on the denominator, so we need to multiply by that on top and bottom. So I've got root 2 over 6 times root 2 becomes 6 times 2, which is 12. Again, there were a lot of steps there, but a lot of that was algebra, stuff that we've done before. My final answer, I'm going to put A and B into this equation right here. I'm just going to put it on the other side of my work because it's kind of busy on this side. So I've got y equals 3 over 2 root 2 over 12 raised to the x. That is really ugly. Often we'll do prettier ones, but I do think it's helpful to do an ugly one together so that you don't always do nice clean ones and then you get kind of a weird one on your own. So I'd rather do harder ones together. Any questions so far? Okay, let's do the next one. Same idea. I've got 0 and 3. Y equals a times b raised to the x. I've got 0 and 3. B raised to the 0 is 1, so a equals 3. Cool, that was a nice one. Now I got to do it again with this new point over here. Y equals a times b raised to the x. A is 3. B is 2. And y, sorry, not b. X is 2, and then y is 6. I don't even have to deal with any fractions here. I don't have to do anything crazy. I'm just going to get that b squared by itself. So 6 divided by 2 is, 6 divided by 3 is 2 equals b squared. And then I just root both of those. Yes, I have another radical here. That's, again, not the cleanest version, but it still works. Oh, something I didn't bring up earlier, but the other class asked about, they said, do we need to put a plus or minus with my b? The answer is no. The reason is we're not, like, this isn't a final answer. This is part of an equation. And if there was a negative in this equation, it would be taken care of in A and not B. So you don't have to put plus or minus. We would never see plus or minus in the middle of an equation like this anyway. We're going to assume that it's positive unless it comes out negative, and then we'll assume that it's negative. So we're going to take it at whatever sign it gives us. And again, we're square rooting here, which is why we asked, but we could cube root or we could not have any roots depending on what's going on. So these are my two numbers. Let's plug it into the end. Y equals 3 times radical 2 raised to the x. All right. Any questions so far?
Was the first problem is like a super hard one?
Mm-hmm.
Like, are the rest of them going to be like this one that we just did?
Some of them are even like give you full numbers. Like I would have maybe gotten like 2 and then like 1/3 or like a real number, not any radicals. So these are both kind of funky ones. Letter A was like really, I think, really hard. So they should be easier than that letter A.
Okay, thank you.
You're welcome. Any other questions you guys have so far?
Is that x with the 2 like outside of it, like an exponent sort of thing?
Mm-hmm. Yep. Yeah, so we're in the exponential unit, so our x's right now are all exponents. All right, any more questions? Okay, we're gonna get into some calculator stuff. So we're doing transformations, which we could maybe do by hand and just like remember what's going on. I wanna walk through on the calculator though, because again, I do think we skip this a lot and I think we assume we know or remember certain properties, and I don't think that's necessarily true. So I'm gonna make this screen a little bit smaller. I'm gonna pull my calculator up. Let me put us down here. Make my calculator a little smaller. There we go. Okay. So I'm going to clear that out, and I'm going to make my standard window, Z6. Okay, perfect. I'm going to graph just the generic exponential function. We learned about exponential functions with BFFs, but you also had 11 other graphs, so I know that you might not have remembered this or committed this all the way to your memory. So let's just look at what a generic exponential graph looks like. So I've got 2 raised to the x. We're going to graph that. So this graph always goes through 0, 1, unless, of course, we're moving up or down or any crazy transformations. But the BFF, the parent graph, always goes through 0, 1. And there's a horizontal asymptote here at 0. I can tell because it doesn't go lower than the negative axis, and it gets closer and closer to 0. That's also just a property of exponential graphs. And so if you didn't remember that, now is a good time to remind yourself, horizontal asymptotes, there's always at least one in an exponential graph. I'm going to sketch this graph just on my paper right now, just so I can go back and look at it later if I want to. Again, it goes through 0, 1, and it approaches this line, and then it goes up. You can draw a little horizontal asymptote if that makes you happy. So this parent function is here. And so we're transforming this graph. So everything we're thinking about is in terms of this. So if we make any changes, it's to this. We're flipping this, or we're shifting it up, or we're moving it left or right. Our transformations are as they've been basically for the past couple units. So if I look at this first one, I've got y equals 2 raised to the x minus 3. Now, since this x minus 3 is all in the exponent, it's like it was in the parentheses of like an x squared graph. Like if I had x minus 3 squared, like this 3 does the same thing both places. When it's in with the x, it means that we're moving it left and right. We're moving it in our x's direction, and it's opposite of what we think. So that means it's going to go to the right 3 units. Instead of going through 0, 1, it's going to go through 1, 2, 3, 1. And let's look at what that is. So I'm just going to go change this graph. Actually, let's do it even better. Let's do it below it so I can see both of them. X minus 3. Graph. Good, so the blue is my original one, the red's the new one, and see how it's just shifted over 3 units? If I were to trace, I would see that at 3, 1, I had a point. For sake of time, I'm not gonna do that. I'm gonna ask you to trust me. It's still approaching my asymptote. It's just moved over a little bit. Again, basic transformations still hold. I just think we're a little less familiar with this, so I'm backing it up with the calculator. All right, the next one says 2 raised to the negative x. So I've got a negative in front of my x. We know negatives flip my graphs. It either flips it up and down over the x-axis, or it flips it left to right over the y-axis. Since it's x, we do over the opposite axis. Whenever you flip something, it's over the opposite axis of what we're doing it to. So since we're doing the negative to x, we're gonna flip over the y-axis. You guys were getting good at this back in unit 2. It just looks different now that I'm giving you an actual equation. So I'm gonna adjust this one. I'm gonna say negative x and then delete everything else. And we're gonna graph that. So again, my red one's the new one. And as you see, it just reflected, it just flipped over my x-axis. I still go through 0, 1. I still have an asymptote at 0, but instead of starting low like I did before, I'm starting high and then I'm going low. Remember that the negative exponent makes it become a fraction. So that makes sense that everything flips. If I had like a fraction, like 1/2 raised to the 8th, that's going to be like a really small decimal. As opposed to if I had 2 to the 8th, that would be like a giant number. So I'm trying to put some like real life into this. Any questions so far? You hanging in there? Okay, let's flip our page. Let's do 2 more on the back. The next one has a negative in front of my 2x, 2 raised to the x. When the negative is out front, that means that it's being done to the y's. It's like all my y's are being multiplied by -1, and that makes me flip over the opposite axis, the x-axis. This time I'm gonna flip down. The last one I flipped left and right. Now I'm gonna flip down and over. Again, let's see it. Let's do -2 raised to the x, graph it. Yep, when I flip it down, it's still approaching the axis where it normally does. Instead of going through 0, +1, it goes through 0, -1. And it would have been approaching the axis over here, and then it would have been getting a lot bigger over here. So that's how I flipped it down. Okay. And then the last one says y equals 0.5x plus 1. Well, wait a second. All of the ones we just did were 2. My base was 2, 2, 2. Now it's 0.5. Remember, though, that 0.5 is the same thing as 1/2. It's really janky, 1/2. Let's try that again. 1/2. So this is the same thing as writing 1/2 raised to the x plus 1. A minute ago, I reminded you that a negative exponent was like writing it like 1/2. It was like flipping it into a fraction. So this does the same thing as the negative exponent, which made us flip over the y-axis. If it was independent, this would be its own graph, but since we're talking about it in terms of that blue graph on my paper already, this 1/2 makes it flip over the y-axis. And then the +1, if you're adding a 1 to the end or minusing something from the end, that affects my y's. So I'm going up 1 unit. I know you can't see that. I'm going up 1 unit. Again, I know that you maybe couldn't see this on your own, which is why I'm explaining it to you. And now we're gonna look at the graph to back that up. So I'm writing for this second one, I'm gonna write 0.5 squared, or sorry, 0.5 raised to the x, raised to the x, and then +1. Make sure if your calculator is like mine, I had to like arrow over to get out of the exponent. So make sure your +1 is big. It's not little like an exponent. All right, let's graph that. Yep, it's flipped over like it was before, but it's up just a little bit. It's up 1 unit. And the graph moves up 1 unit, but so does my asymptote. So my asymptote is no longer at 0, it moves up with us. Since it's horizontal, it can move up and down. It doesn't move left and right because it's still the same line, so that doesn't affect it. Horizontal shifts don't affect it, but vertical ones make it move. So now that's at 1, and I am flipped, so I did start over here, and I go like that. I would challenge you to start recognizing what these transformations do on your own, but then also back it up or confirm yourself with the graph. And the more of these you do, the more of them make sense. All right. Any questions so far? Okay, we're doing similar stuff now with number 5. It says state whether f of x represents growth or decay, describe its end behavior. So we're gonna look at graphs again, and we're gonna look at end behavior. We're gonna use our limit notation for that. So the limit notation, we did briefly last unit. We write limit of f of x equals, and it will be like some number. Most of the time it's 0, 1, 2, or positive or negative infinity. And we have to do x approaches negative infinity and x approaches positive infinity. So we'll look at that in 1 second. What I do want to do though is my graph. So let's graph these. I'm going to put them all in my calculator, but we're going to look at them one at a time. So I'm going to do 3 raised to the x, 3 raised to the negative x. You are always welcome to graph with me. You're also welcome to just watch. Again, I'm putting this online so you can watch again if you're like, I'm still not really sure how she got what she got. And that also allows you to like pause, rewind, all that stuff, because you can't pause and rewind me in real time, unfortunately. Okay, I've got all my graphs in, but I'm going to turn off all the ones except for the first one, just so I don't get too confused with too much going on. So I've got 3 raised to the x. This is going to be the exact same as my 2 raised to the x, but if you notice, it's a little bit steeper of an increase than the 2 was. So it just goes up just a little bit quicker. 3 raised to the x, growth versus decay. As I move across the page, as you read, just like you would read a book, I think about, is it increasing as I go across the page from left to right, or is it decreasing? In this case, it's increasing, which means that it is a growth. Okay. Now, I don't need to show that part of the calculator. Now I'm going to do my limit notation. So I'm going to write this over here. So I've got the limit of f of x as x approaches negative infinity is something. And then I'm going to write the limit of f of x as x approaches positive infinity is also something. Again, when we do limits, when we do limits of our function, we're looking at what we're getting closer to as we get closer to the negative or positive side. If you see, I'm gonna try and draw, but we'll see if that works. You see over here, that's where my negative infinite, where my negative x's are going towards, like, off the graph. And they're getting closer and closer to 0. They're never going to go lower than 0. They're not going to increase. They're getting closer and closer to 0. So the limit of my function as x approaches negative infinity is 0. Similarly for positive, oh no, undo. For the positive numbers, that's all of these over here. Like this. These are all my x's, and my y is doing this. It's going up, 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 even off the calculator. So that means the y's are getting bigger and bigger. I'm approaching positive infinity. Questions so far? Let's do a couple more. Maybe any questions will arise, or maybe you'll understand. So now I'm going to go back over here. I'm going to do my y equals, and I'm going to put it in for my second one. I want to graph my second one. Again, you can graph these all individually. I just trying to do what's most time efficient. So now I just pressed on for the 3 raised to the negative x. It's just like the one we did, but it's flipped. So now it was increasing, or it was really high when we first started, and then as we keep going across the page, it gets closer and closer and closer to 0. So it's just flipped over the x-axis. It's flipped over the y-axis. My growth or decay, well, it's going smaller, 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 smaller as we go across the page. So this is a decay graph. Again, I'm going to do my limits. So I've got I'm going to write my limit notation. Limit as f of x equals, x is negative infinity. And then we'll do it for positive infinity. Again, I'm using my little draw tool. So as x is smaller and smaller, so these are my negative values, y is getting bigger and bigger and bigger. It's increasing. So we're going to say that my limit of my function as x approaches negative infinity is positive infinity, because I'm going to all the positive y's over here. No, that's not what I want. There we go. Okay. Now I'm going to do for x is approaching positive infinity. Similarly, I've got my, okay, trying something new and it's not working as well as I wanted to. That's all right. As my x's get bigger and bigger and bigger, my y is staying constant. It's getting closer and closer and closer to 0. So I'm approaching 0. Hint, all of these will approach 0 or they'll approach one of the infinities. If the asymptote is not at 0, then it approaches that asymptote, but we're always approaching, and you can even think of this, we are approaching a horizontal asymptote and one of the infinities. It just depends on which direction we're going in. So that's
Miss White.
yeah.
So like when we're trying to find the limits or whatever as it equals negative affinity and positive affinity, so it will never be like a definite number like 2, 3, 4. Is it gonna always be like 0 or infinity because we're finding the asymptote?
If the asymptote is at 3 or 4, then it would be that. But in most cases, so 0 is common.
Okay.
Yeah, good question. And we'll do examples of those later, but all the rest of these are all at 0. All right, so let's do 2 more. We've got 1/2 raised to the x, so we're gonna kind of fly through this a little bit more. I'm gonna do my third graph on, put my second one off. This one is going down again as I go across the page, just like the one I just did. And because they have the same asymptotes, their limits are also going to be the same. As x was approaching negative infinity, my y's were getting bigger. We started over there where the y's were big. And then now as we get closer on the positive x side, I approach 0 again. So my limit notation is exactly the same as the last problem. And again, that reason is because my asymptote is the same and they're both decay graphs. So I was approaching, positive infinity for my negative y's. That was positive infinity. And then now when I do my positive x's, I'm approaching 0 because now I'm getting closer and closer to the axis. So if you notice here, we've got a negative exponent and then we have a fraction. Those give us the same idea kind of graph. Those are related to each other. They're both decay. They give us the same shape. The last one, if you can kind of tell where we usually head with these kind of things, it's going to mirror the first one. So a fraction with a negative exponent or a decimal with a negative exponent is going to mirror the same idea as just a full whole number with a positive exponent. This is another growth graph because as I go across the page, it's increasing, which means that my end behavior, my limit notation is going to be the same as it was on the last one. Or not the last one, the very first one. When x was negative, y got closer and closer to 0. And as x got bigger and bigger, y also got bigger and bigger. So we're going to do limit of f of x as x approaches positive infinity, that is positive infinity. And again, horizontal asymptote and one of the infinities. This time all of our examples were positive infinity. I hope to do other examples later, but that's what we got for today. Any questions so far?
Are the limits for the growth and decay graphs, like, are they always going to be those ones that we just did, or no?
So if it was like on the negative side over here, we didn't do anything where it was down on the negative axis, so that would make it a little bit different. But if it's in the positive axis, your growth and decay graphs will always have that end behavior.
Okay, thank you.
You're welcome. Okay, we got about 4 more minutes and I want to do one more type of problem. This last one right here that looks really confusing because this is the logistic graph. Logistic was one of those BFFs, and I think I told you it was one that I thought was kind of dumb. I have a degree in math. I've never looked at a logistic function past algebra 2, early pre-cal like you guys are right now. You will never look at this again, even if you have a degree in math. I think it's dumb, but we're still going to study it. We're going to want to find our x-intercept and our horizontal asymptote. Your x-intercept is, or sorry, your y-intercept. Your y-intercept is just like we've been finding before. We just plug 0 in, trying to go a little too fast, 0 in for all my x's. We just replace all the x's with 0 and then we solve. So let's do that and then we'll do horizontal asymptote. So for the first one, I have 12, that didn't change, and I've got 1 plus 2 times 0.8 raised to the 0. Well, remember anything raised to the 0 becomes 1. So that means I've got 12 over 1 plus 2. Oh, well, 1 plus 2 is 3, and 12 divided by 3 is just 4. That was pretty easy. Let's do another one. Same idea, plug 0 in for your x. I know I'm raising like these decimals, these funny things to 0, but because I'm raising them to 0, they cancel out and they go away, which is so nice. So I get 18 over 6. Oh, I went a little fast. 5 plus 1 is 6. And then 18 divided by 6 is 3. Last one, same idea. I'm raising e to the negative 0. Well, negative 0, positive 0, they're the same. Cancels out, so I get 9 over 1 plus 2, which is 3. And 9 divided by 3 is also 3. Okay. Now, horizontal asymptotes, when we did rational functions, we had to look at some exponents. This, you only have to look at the equation, and I'm just going to graph it for you to prove a point. You will not have to graph these in the future. If I graph 12 divided by 1 plus 2 times 0.8 raised to the x, all my parentheses in order, I'm going to make sure my window goes to a max of 15 because I'm showing you a point that I know. The logistic function was that kind of that S-shaped function from our BFF graphs. It looked like this. And again, I thought it was kind of dumb. You have an asymptote at 0 always, 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 always. And then this top asymptote depends on the number on top of your fraction. If we were to trace here, I'm going to trace and I will never reach 12. Watch. 5, 6, 7, 8, 9, 10, 11, but it's going to take me forever. I'm never going to get to 12 even if I hold this down for the rest of the time I hold you here. You don't ever have to graph this. I just graphed it to prove a point, but your horizontal asymptotes for all of these is going to be just the numerator. My horizontal asymptote is at y equals 12. My horizontal asymptote is at y equals 18. Always, 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 by rule. I know I'm almost done. So horizontal asymptote is the numerator. Okay. I know I kind of sped through that last thing. We'll touch on it again on Friday if you have any questions. But does anyone have any questions on what you see right now? Okay, I'm going to stop share. I'm going to stop record. I have not finished this unit.